Hi everyone. I decided to split this week's video into two parts. So this is the first part of the lesson on the color of sunsets. So watch this first. And the second part on rainbows and fiber optic cables is coming up next. See you there. Bye.
Hi everybody. Welcome back. We're going to continue talking about refraction this week. I would like to talk about some of the applications of some of the physics we've actually discussed. As you recall, we talked about how refraction of light occurs when light enters a material, and that material changes its speed, slows the light down, causing the light rays to change directions. So we're going to review a little bit of that material this week and apply it to understanding some common phenomenon in our lives. So let's get to it. All right, again, you'll recall that refraction is caused when a material changes the speed of light. So here I have two materials, air and glass, and the red arrow represents a light ray. In this case, the incident material is air, it's where I'm starting from, and I'm traveling into glass. And I've drawn a normal line where the light ray is striking the boundary as it crosses from air into glass. Well, the velocity of light in air is basically c. As we talked last week, we said air doesn't slow light down much at all. So to first approximation, we can just treat it as 3 times 10 to the 8th meters per second, the same as light in vacuum. But glass is a different story. Glass, the atoms are much more closely spaced, the electrons are interacting with the light wave a lot more, and so glass will have a significant effect on the speed of light, slowing it down a good deal. So the velocity of light in glass is going to be much less than c. So we illustrate that by calculating the index of refraction. Remember, the index of refraction was the speed of light in vacuum, c, 3 times 10 to the 8 meters per second, divided by the velocity of light in the material. So air, n equals 1, in reality it was something like 1.000007, but very close to 1. And because the velocity is basically c. But in glass, the velocity is smaller than c, and so my index of refraction is larger than 1.5. In fact, remember, the index of refractions always have to be larger or equal to 1 because nothing can go faster than the speed of light in vacuum, c. So if this glass had no effect on the light ray, it would simply go straight into the glass. But that's not what we see. And you can check out the demonstration video that I've done this week to see actual light being refracted in the glass. But what happens is the light slows down, that change causes the direction of the wavefronts to pivot, and I have refraction occurred, and the ray changes direction in the glass. In this case, bends towards the normal line. In fact, we mentioned that when the speed of light decreases going into a material, it will bend towards the normal line, bend inwards. But if I reverse the materials, if I end up going from a slow material into a fast material, as the light speeds up, the direction of the light ray would bend away from the normal line it would bend outwards instead of in. Okay? All right, so basically this week I want to look at 3 phenomenon. So the 3 phenomenon we'd like to look at this week. 1, why are sunsets or sunrises, why do they always appear red to us? We know the light produced by the sun is producing all different wavelengths, mixing together to make white light. Why at this time of day does it seem the sunsets look red or sunrise always looks red? We'd like to see why rainbows happen, so we're going to examine why we see rainbows why it's possible to see rainbows after a spring or summer storm. And I want to talk about total internal reflection, which is key to a piece of technology that is incredibly important to our lives, fiber optic cables. And you probably aren't aware of it, but you're using fiber optics in your life right now. So we'll talk a little bit about total internal reflection and how the uses of fiber optic cables. All right, so we're going to start with sunsets. That's probably the more straightforward of these 3 topics. All right, before we begin, also we talked about, we should recall how refraction also causes this phenomenon of dispersion. So here I have a glass prism, and I'm going to send in white light. Now, white light is a mixture of all the colors of the spectrum, and what I see coming out is these colors, the mixture of colors are now separated out into their individual components, and instead of saying white light, I see the entire spectrum, Roy G. Biv. And we talked about how this was caused because the index of refraction is actually slightly different for each one of these colors. That although the index of refraction for the glass is about 1.5, each wavelength, each color will have a slightly different one. Red has the smallest of the index of refractions, that's 1.509. Yellow is a little bit larger, and by the time you get to violet, the index of refraction is 1.521. That means that the violet light has a larger index of refraction, so slows down more than the red light. The red light is traveling faster than the violet light inside the glass. That also means that the violet light is going to undergo more refraction and be bent slightly more than the red light. All the light is getting bent inside the glass, but violet will bend the most, just a little bit, because the index of refraction is a little larger. With these two things in mind, let's examine what happens during a sunset. There you go. So violet light bends more in glass than red light. So here we have a picture of the Earth and its atmosphere. Now, nowhere near drawn to scale. So this blue layer here represents the atmosphere of the Earth. In reality, at this scale, we would barely be able to see the atmosphere. Depending on how you want to measure it, the atmosphere extends anywhere from 40 miles, 60 miles or so above the surface of the Earth, depending on where you want to call, how thin you want to get before you can call it no atmosphere. So this is an exaggeration for the thickness of the atmosphere. So we're looking at the United States. Let's put an observer in the United States somewhere close to Massachusetts. Here is our observer, also not drawn to scale. And the sun is overhead. So I'd like to see what happens to the rays of light coming from the sun when the sun is overhead first. So let's send a ray of light from the sun to the Earth. The first thing that's going to happen is going to strike the atmosphere. Now, we've been treating the atmosphere, the speed of light in the atmosphere the same as the speed of light in vacuum because it doesn't change very much. To 3 sig figs, it's 1.00 is the index. But we saw last week that is actually slightly, very slightly larger than 1, which means the air has a slight effect on the speed of light, and the light will slow down just a little bit as it goes from space into the atmosphere, which means it's going to undergo refraction. So I need a normal line so I can see what's going on. Now, the atmosphere makes a sphere around the Earth, and as we talked with spherical mirrors, that means that the normal line is going to go from the edge of the atmosphere to the center of the Earth, and I've drawn my normal line accordingly. Now, when the sun is so high in the sky, I don't have a large angle of incidence. Remember, we're measuring that from the ray to this normal line. It doesn't have a large angle of incidence. It has some, and the air slows down the light a little bit, so there will be some refraction. But not a lot, because the air doesn't slow down light that much, and I don't have a big angle of incidence to begin with. So when the sun is high in the sky, you have a small angle of incidence, so not a lot of refraction or dispersion. But that's going to change as the sun gets lower in the sky for a sunset. So let's take a look at that situation. So towards sunset, or sunrise, if we look at the other side of the day, the sun is lower to the horizon. So again, I'm going to send a ray of light from the sun to the air. And again, it strikes the surface of the atmosphere. And again, I'm going to need a normal line. So here's my normal line extending from the center of the Earth to the point where the light is striking the atmosphere. And you see now that I have a much larger angle of incidence measured to the normal line. Not just that, the light has to travel through a much longer distance through the air. When it's overhead, it's only traveling through the thickness of the atmosphere. But here, because I'm hitting at an oblique angle like this, it's going to travel a lot more in the air, so the air is going to have a larger effect on that light. Since I have a large angle of incidence, I have a larger angle of refraction, I have more bending, but also I will have more dispersion because it's traveling further through the air. That is, the air has the ability to start separating out the individual colors of the light through Roy G. Biv. So that means that as the sun gets lower and lower on the horizon, The higher frequencies, that is, the color is closer to violet, are getting bent more and more than red. So as the sun gets lower and lower, you're going to be seeing a larger proportion of red light striking your eyes. The lower the sun goes to the horizon, the larger the proportion of red light striking your eyes compared to the other colors. Until finally, as the sun drifts below the horizon, the only light that will be able to make it to your eyes are in the red wavelength. All the other colors will be being blocked by the earth as the sun gets lower and lower in the sky. Hence why sunsets always appear red. So as the sun moves low to the horizon, you're more likely to see these faster red rays because they don't bend as much as the slower violet rays. And so therefore the last colors you see during a sunset, or the first colors you see during a sunrise, will be the reds. And so the sun will appear red. Alright, so that was pretty straightforward. So let's talk about why rainbows appear, but that's a little bit more complicated. So first we need to talk a little bit about Snell's law again.